First of all, what is a digital image? So in this case, our image is being recorded as a numerical array of pixels. So though we're seeing an image, it's actually essentially an Excel spreadsheet. Each pixel has two different characteristics defined. First is its size, or its equivalent size in the image. And in this example, you can see that the pixel has a size of 100 nanometers. And we also have a gray level, which is our intensity value. And in this case, we have an intensity value of 108. So the two characteristics we're looking at here are sampling resolution and also bit depth. So what is bit depth? It's basically the number of grayscale values that we're going to split up each individual pixel into. So what intensity ranges there are. So in a 1-bit image, you've got 2 to the power of 1, which gives you 2 colors. This means there's either 0 intensity or maximum intensity. And this is what we call a binary image, and we'll use those in the FIJI for quantification workshop. For a 2-bit image, that gives us 2 to the 4 grayscale values, which is going to give us 4 gray levels. 3-bit is 2 to the 3, which gives us 8 gray values, and then 4-bit is 2 to the 4, which gives us 16 gray values, etc., etc. What does this mean? So here we've got a zoomed in region of 2x4 pixel arrays, and on the image on the left, this is saved on an 8-bit scale, which goes from 0 to 255 grayscale values. And you can see the 2 pixels which have been highlighted have the exact same intensity values. If we take the exact same data but we save that as a 16-bit image, then you can see we can now start to differentiate the intensities between these 2 pixels. And that really becomes important when we start to look quantitatively at the data. Another example of this I thought we could use is to take an actual microscope image and present that as a 1-bit image, so either 0 intensity or maximum intensity, a 2-bit image, a 3-bit image, and a 4-bit image, and then finally an 8-bit image. And you can see at each of these steps we're seeing more and more information. If we now take a line profile and look at the intensity along that yellow line in the image, and this is again one of the things we'll do in the FIJI for quantification workshop, we can see that as the bit depth increases, again we're getting a lot more quantitative information. So in the 1-bit image you can see it's either 0 or 255. By the time we get to the 8-bit, you can see a lot of information going on. So how does that equate to microscopes? So a lot of the detectors that we're using can come, if they're, for example, a camera-based detector, they'll have a set bit depth. So you'll often hear people talking about a 12-bit camera. If you're using a confocal system, then we can actually sometimes change the bit depth that we're recording the data at. So as I already mentioned, 1-bit image is giving us 2 grayscale values. That's using creating a binary mask that we can use for image analysis. A lot of common microscope detectors are 8 bits, which gives us 256 grayscale values. But you can go up, as you see, up to 32-bit images, which is giving us well over 4 billion grayscale values, which is probably more information than you really need. The take-home message here is if you're just taking an image for visualization purposes, for putting in a presentation, then 8-bit is probably fine. If you're going to do any quantification, then you might want to increase that bit depth up to something like 12 or 16-bit. The only difference it's going to make is the size of your file, so it shouldn't take any longer to acquire the data.